Welcome. Let's understand neutral grounding techniques. Neutral grounding techniques can be classified into the effective neutral grounding or solidly neutral grounding method, and the non-effective neutral grounding method. The difference between the two practices is the difference of the zero-sequence circuit, from the viewpoint of power network theory. Therefore, all power system behavior characterized by the neutral grounding method can be explained as phenomena caused by the characteristics of the zero-sequence circuit. Neutral grounding methods have a wide effect on the actual practices of various engineering fields, for example, in planning or operational engineering of short-circuit capacity, insulation coordination, surge protection, structure of transmission lines and towers, transformer insulation, breaker capability, protective relaying, noise interference, etc. In this video, some typical features of different neutral grounding methods are presented. The neutral grounding method of power systems can be classified as follows. A. Effective neutral grounded system. Solidly grounded system. B. Non-effective neutral grounded system. Resistive neutral grounded system. Arc-suppression coil, Peterson coil, neutral grounded system. Neutral ungrounded system, may be called neutral minute grounded system, but only adopted for distribution systems. Solid grounded system versus non-effective grounded system. For the effective grounded system, grounding fault currents can be increased considerably, but on the contrary lower temporary overvoltages would be caused during faults. Solidly grounded systems all over the world, mainly to realize EHV or UHV networks with reduced insulation levels. For the non-effective grounded system, grounding fault currents can be reduced considerably, but on the contrary higher temporary overvoltages would be caused during faults. The largest feature of the non-effective neutral grounding method is that the continuous or temporary earth, ground flowing current, is considerably reduced under normal or fault conditions. Its greatest advantages, in particular for distribution systems, concern human security and suppression of noise interference. These are quite important matters, especially in residential areas covered by distribution networks. Question: can we change the existing neutral grounding method of existing networks? Let's see the answer. Changing the neutral grounding method of existing networks is practically almost impossible, because major modifications or reform of existing engineering practices would be required. For example, the basic design of substation earth grounding practices, grounding varied mats, counterpoise, etc., would have to be revised. Most arresters, protective relays, and some other substation equipment would have to be replaced, and so on. Question: can we adopt solidly grounded method in the lower voltage or distribution networks? Let's see the answer. Remarkable reductions in the system insulation level, or cost by adopting the solidly grounded method, cannot be expected in the lower voltage or distribution networks. In case of the lowest voltage network of 100-400 volt, typical example, the insulation level may not be able to reduced by adopting solidly neutral grounded method instead of high resistive neutral grounded method, because reasonably marginal toughness and high human safety factors rather than lower insulation levels are inevitably required for these voltages classes, such as mechanical strength, thermal strength, as well as long durability. Similar situations may be seen in distribution systems of 30 kV or lower. Various neutral grounded systems. A. Solidly neutral grounded system or effectively neutral grounded system. All the transformers installed at substations, belonging to the same rated voltage are solidly neutral grounded. B. Resistive neutral grounded system or impedance neutral grounded system. All or some selected key transformers, installed at substations belonging to the same rated voltage section, are neutral grounded through a neutral grounding resistor. The resistive value of Ngr is determined mostly so that the grounding current through the Ngr in one phase to ground fault is limited to 100 ampere or within 1000 ampere. Arc-suppression coil neutral grounded system, or resonant neutral grounded system. Some key transformers are neutral grounded through tap-changeable reactors, whose taps are selectively controlled, so that the inductive reactances are well tuned, with the capacitive reactances of transmission lines over time. The zero-sequence circuit is kept under parallel quasi-resonant conditions, and the zero-sequence impedance of the systems have quite large values, therefore quite effective arc extinction can be expected during one-phase to ground lightning faults. Resistive neutral grounded system with neutral compensation reactor. Here the neutral compensation reactors are equipped to compensate for stray capacitances of the transmission line, in particular of long transmission lines or cable lines. Neutral ungrounded or isolated neutral ungrounded systems. This is a typical practice, which is adopted only for distribution networks. In this system, intentional neutral grounding connections do not exist, except through potential indicating or measuring devices or other very high impedance devices. The grounding current caused by one phase to ground fault would be limited to values of 10 mA to 1 ampere by a large neutral impedance, the order of a few thousand ohms or more.